Here's a quick fluid mechanics question which refers to the topic of momentum conservation. Now, this is something that you might actually see as a first year engineer. And if you want to see anything like this in the future or any topic related to maths or physics or any specific problem, feel free to let me know in the comments. So let's read this and let's see how to approach it. So we've got a water tank which is sitting on a cart which is on wheels, and the cart is attached via a cable to some wall, right? And then there's a hole in this tank, and there's water coming out of that. And then there's this sort of deflector, well, it's a vein actually, and the water is deflected at 60 degrees with respect to the horizontal. And we know that the water leaves with a velocity of 8 meters per second. So the question here is, what is the tension in that cable, in the supporting cable? And the easiest way to do this is, of course, to draw a control volume. And the way you would, or the easiest way to draw the control volume is to include the entire tank, and then you would cut through the cable like this, right? So by doing that, you can now actually draw all the forces acting on the control volume, right? Which is, well, in this case, the only force that's relevant is the tension, right? Which is acting through the cable and it's pointing to the right. And other than that, we have the water jet leaving our control volume at an angle of 60 degrees, something like that. Right, so this is the velocity. Let's actually call this u equals 8 meters per second, and we know the angle of 60 degrees as well. So in this case, to find the tension, we just write the equation of momentum conservation, which is that the change in momentum flow rate, so that would be momentum dot, that is equal to all the forces acting on the control volume, and we're only looking at what happens in the x direction, right? Because the tension is acting in the x direction, so we're only considering the momentum component in the x direction. So the change in momentum flow rate is actually equal to the flow rate of momentum out in the x direction minus the momentum flow rate in also in the x direction, right? And this is equal to all the forces acting on the control volume in the x direction, which in this case, it's just the tension. So let's actually treat each of those terms separately and let's see what they are. So the momentum flow rate in the x direction is due to this water jet leaving the control volume at an angle of 60 degrees with a velocity of 8 meters per second. So let's maybe try finding out the mass flow rate first. Yeah, so the mass flow rate is given by the usual formula, which is rho A times U. So what I'm doing now is I'm looking at the mass flow rate through this orifice, right? Because the diameter of that water jet stays constant, and because water is incompressible, in other words, the density is constant, it means this velocity of 8 meters per second is the same here where the orifice is located. Okay, so we can find the mass flow rate in this way, and that is rho, and then the area is just pi over 4d squared, right? Or pi r squared if you want to calculate the radius first, and then that times u. Okay, so this is the mass flow rate, and let's see how we can use this to find the two momentum terms. Okay, so the momentum out, the flow rate of momentum out rather, in the x direction equals, so that would be the amount of momentum leaving the control volume, okay? And we have that the momentum, the water, the jet leaves the control volume here. So the momentum flow rate is going to be equal to the mass flow rate multiplied by the velocity, and then we have to take the horizontal component of that of those 8 meters per second, right? And to do this, we take the cosine of 60 degrees. So what we're actually doing here is we know that the velocity is going at a 60-degree angle. So to find the x component, like the ux, um, the x component of the u velocity, we just take the cosine of 60 degrees. And this is what we get, right? And we know what the mass flow rate is from the previous equation, which is rho and then pi over 4 d squared u, right? So I'm going to put this in brackets because this is the mass flow rate, okay? And then this is multiplied by u cosine of 60 degrees, okay? Which turns out to be, so I'm going to rearrange a couple of things. So we have pi over 4 rho d squared u squared, and then cosine of 60 degrees is actually a half. So the final, well, not really the final result, but if we tidy this up a bit, this is pi over 8 rho d squared and u squared. Okay. So this is how much momentum comes out per second from the control volume in the x direction. Okay, this is the momentum out x, and now we're gonna find an expression for the momentum in, so the momentum that goes into the control volume in the x direction. And if you look at how we drew the control volume, there's actually no momentum coming into the control volume in the first place because all the water is inside that tank, right? And there's only water leaving the control volume. So it's safe to say that this quantity is actually zero, okay? Which means that if we go back to this equation right here, we can find what Fx is, right? But remember Fx, which stands for all the forces acting in the x direction. In this case, it's purely referring to the tension. So that would be tension equals, and we have momentum out that we found here. So that's pi over 8 rho d squared u squared minus momentum in, which is 0. So it's redundant to write 0, and that's the expression, that's the equation for tension. So we can just put the numbers in. So we have 1,000 for density because we're dealing with water. The diameter, I think, was 4 centimeters, so we turn that into meters, we square it, and then the velocity is 8 meters per second, and we square that as well. And the result will turn out to be somewhere around 40 newtons, right? So this is the force required to keep the water tank in place. Okay, and that force is actually the tension in the cable, and the tension is due to that momentum leaving the control volume. And that's the end of the question.